Partha is working at NanoMEGAS as an application scientist. He's based in Spain, and he has worldwide responsibility for diffraction, tomography, and EPDF, including applications, training, and customer support. It's all yours, Partha.
Hello, I am Partha Pratim Das, and thanks Robert for the introductions, and thanks everyone for joining the webinar on structural characterizations in TEM by 3D electron diffraction. Actually, I started my scientific journey with X-ray diffraction, but for last few years, I have been working on electron microscopy based techniques, diffractions based techniques more specifically. In these presentations, I will show some of our work and the journey of many other scientists in this field. So actually, structural analysis by 3D electron diffraction was started in the West in 1976 by an American scientist, Douglas Dorset. And what informations one can really obtain using 3D electron diffraction? Let me show you an example from one of our recent work. Once there is a crystal, one can acquire 3D electron diffraction data. From the 3D electron diffraction data, one can determine the unit cell, symmetry, and extract intensities. And once intensity is extracted, one can find all the atomic position present in the structure, as you can see here. Now, there are different methods for extracting structural information from a crystalline material. Most common method is X-ray diffraction, but with single crystal X-ray diffraction, one needs at least 1 micrometer crystal or larger. For powder diffractions, though the crystal size requirement is small, but if there are more than one phases present in the material, extracting the structural information is extremely challenging. Other possible method to extract structural information is by X-ray femtosecond crystallography or free electron laser. But each of these methods have their own challenges. When facing such a problem, the method of choice could be 3D electron diffraction in TEM. Because if more than one phases is present in the sample, it is not an issue anymore to study in a TEM, because we can study individual small single nanocrystal. In TEM, also we can perform spectroscopic and chemical analysis at the same time, which is of really great benefit. Now let me show you an example from recent publications to better understand what size of crystal can be used in the TEM. As you can see in the magnified image of the crystal, the purple colored circle is required for doing a X-ray diffraction data in a microfocus beamline in ESRF. And on the top, you can see the yellow dot, which shows the size of the crystals required for 3D electron diffraction. Then it shows you that what size of crystals you really require for a 3D electron diffraction study. Now, what are the major differences between X-ray and electron diffraction? As you can see, for electron diffraction, UV sphere is flat in comparison to the X-ray, because of the very short wavelength used in electron diffraction. That means one can collect sections of the reciprocal space in just a single shot. Also, we know once the crystal size becomes smaller, the diffraction patterns becomes very broad. As you can see in this example, with crystal size smaller than 10 nanometers, the diffraction pattern is extremely broad. It is known as X-ray amorphous, but the size of the crystals, this size of the crystals we can study in a TEM to obtain suitable structural informations. Now, in case of electron diffractions, the interactions of the beam with the crystals is extremely strong, and that makes the diffraction patterns more dynamical, means non-kinetical, which precisely means the intensity modulations in the diffraction pattern gets messed up. And additionally, one can see more spots which should not be present due to systematic absences. Then there is a technique to minimize these dynamical diffractions in electron diffraction experiment, which is known as precession or precession electron diffraction. The method was first proposed by Vincent and Nickley in 1994. I will show you later what precession technique actually means, but first let's see the effect of precession in electron diffraction. For a cubic mineral, First, a conventional ED data was collected. Then a second ED data was collected with precision technique in the same orientation. And two obvious things you can see. First thing, there are more spots in high angles where the data was collected with precision. And second thing, there is intensity variations in the diffraction patterns. Now, if we compare the precision electron diffraction data and conventional ED data with the kinematically simulated data, we can see that ED data collected with precisions matches much more closely with the simulated kinematical data. Let me show you another example. For a cubic mineral, ED data was collected different precision angle, and you can see by increasing precision angle, the intensity variations in the diffraction pattern shows up again. Hence, to summarize the benefits of using electron diffraction patterns, intensity variations in the diffraction pattern stays like the kinematical one in case precision is used. That helps in the right symmetry determinations, and it helps in the structure solution process. Now, as I mentioned before, I'll show you what actually precision technique means. In precision electron diffraction techniques, a tilted incident beam is rotated very fast around the central axis of the microscope. And subsequently, an electron diffraction pattern is formed by integrating the orientations in different directions. NanoMEGAS have designed a dedicated hardware to do a beam precisions, which is commercially known as Digistar, and it is compatible with all the electron microscope, transmission electron microscope present currently in the market. And it is almost used by 50 labs in US itself. Now, what are the different steps to obtain a structures from a 3D electron diffractions data? First step is to do a sample preparations and align the TEM for a diffraction experiment. Second step is to collect 3D precision electron diffraction data using the hardware developed by NanoMEGAS. Third step is to determine unit cell symmetry and extract intensities from the collected 3D electron diffraction data. This can be done with a dedicated software like ADT3D, supported and provided by NanoMEGAS. Fourth step is to do a structure solutions using the data you have already extracted. And for this, software like IANA or SIR can be used. The structure solutions process can take a couple of hours to days depending upon the complexity of the structure. Fifth and the last step is to do a refinement of your structures. Usually kinematical refinement is done. In most of the cases, this sort of refinement is sufficient enough to solve a structural problem. And there are many softwares to do this refinement. Mostly we use IANA, Selex or C software. In the remaining slides, I will discuss each of these steps, especially the step 1 and step 2, to better understand what are the different methods of sample preparations and what are the process to acquire 3D ED data. Actually, there are different standard and non-standard methods for doing sample preparations, as you can see. Some of them are suitable for material science applications, some of them for pharmaceutical applications, some of them for macromolecules. Instead of going through all the different sample preparation method individually, I will mention in the examples, application example, which methods we have been used for which type of materials analysis. But the most important thing everyone needs to keep in mind, the sample should be beam transparent for an electron diffraction experiment. And for the TEM settings, the electron diffraction data can be acquired in the TEM or STEM mode. STEM mode with low temperature conditions are recommended, especially if we are working with beam sensitive materials. Because in the STEM conditions, one have a much lower electron dose than the TEM mode. Now, for the sample holder, one can use single tilt holder. One can also use cry holder, especially if someone is working with beam sensitive materials. For unit cell determinations, a smaller tilt range plus minus 30 degrees is good enough to obtain reliable results. But for structural solutions, a much higher tilt range is required. The required tilt range usually depends on the symmetry of the crystal. In 2016, using direct electron detection camera for the first time, we have solved organic structures of carbamazepine and nicotinic acid at room temperature. The result obtained by electron diffraction matches perfectly well from single crystal X-ray diffraction data, and this result was highlighted by International Union of Crystallography. For more details of these results and analysis, you can see the publications mentioned in this slide. Next, the step 2, to acquire the three-dimensional electron data. So to acquire the 3D electron diffraction data in TEM, first one has to find the crystals in the TEM grid, which is beam transparent and separated from the other nearby crystals. Only then one can start collecting the data, either by tilting the crystal in stepwise or doing a continuous rotations of the crystals. Electron diffraction data usually are acquired with beam precessions to get a better quality data, which I've already mentioned in the few slides before, and that's what we always recommend. During the tilting process, usually the sample moves away from the beam, then we readjust the sample manually, and once this data acquisition process is finished, we obtain a three-dimensional electron diffraction data. The data acquisition process is usually highly reproducible, robust, but it may sometimes acquisition time is very short, close to minutes, but sometimes it takes hours depending upon how challenging is the sample. The technique of collecting 3D electron diffraction data was actually first proposed by Ute Kolb in 2007, and it is known as automated diffraction tomography. Since then, there have been many different variants of the same method proposed by different authors for collecting 3D electron diffraction data. One of them is collecting by continuous rotation of the crystal. This method of rotating the crystals continuously for data collections was first proposed by Nederlof et al., who is currently working with one of the major TEM manufacturer, and subsequently the same method was proposed by Tamir Gonen and other scientists as well. As all of these methods are variations of the same technique proposed by Ute Kolb et al., we will call all of them 3D electron diffraction throughout my presentations. And you can see also more details about acquiring 3D electron diffraction data and different terminology of used in 3D electron diffraction data acquisition process in a recent article of ICS Central Science. Now, actually, as I said before in the first slides, data acquisitions, structure solving by electron diffraction data has been started from 1976. But in 2007, there was a special issue on structure solutions by electron diffraction, more precisely by precision electron diffraction. Then from 2009, there was a huge boom of solving structures in combinations with 3D electron diffractions with precisions. And in all these years, more than 150 structures have been solved. Also, on all these years from 2009 to 2020, different types of structures has been solved, as you can see it here, and some of which I will present in the remaining part of my presentation. So now, once you solve a structure, one of the most important things which comes to the mind of a scientist, how precise is my result? How precise is the structure solved and refined by 3D electron diffraction? For this purpose, I have taken an example from our work on 3 different materials where structures were solved and refined using 3D electron diffraction data. In the last column, marked in red, you can see the difference between the atomic coordinates of the solved structures by electron diffraction and structures solved for the same material by single crystal X-ray diffractions. And you can see that by doing a structure solutions from 3D electron diffraction data and doing a kinematical refinement, one can get a structures of 10 picometer accuracy or 0.1 Armstrong accurate structure. Now, in the next 4 or 5 slides, I'll cover 4 examples selected from our work and where 3D electron diffractions has been applied. First one is a zeolite example where it was not possible to grow any large single crystal of single phase, which is suitable for single crystal X-ray diffractions. Neither it was possible to extract any structural informations from the synchrotron powder diffraction data. In this case, 3D electron diffraction methods we have applied. Sample we prepared by simply crushing the sample, crushing the material, and data was collected by continuous rotation of the crystal from a small crystal in combinations with beam precisions. From the obtained data, we find the unit cells and the symmetry, and ultimately solve the structures. And also we have do a read-field refinement of the obtained structures from electron diffraction data. The data collections was 3 minutes, close to 3 minutes, and due to reduce the beam damage, and the work we have published in JACS in 2016. The second example, the example is not from my work. Second example is studying the nickel diffusions of a gallium arsenic nanowire by thermal annealing in nitrogen-rich temperature. First, an EDX was performed, and from the chemical analysis, 2 different phases across the nanowire was observed. And then the author moved to 2 different locations where there are 2 different compositions. 3D electron diffraction data was acquired in stepwise mode with precision, and unit cell was determined, and the obtained unit cell from these 2 different locations matches well with the X-ray result from the bulk material. Then from this 3D ED data, it was also possible to solve the structures of these 2 different phases. In this case, EDDT acquisitions, electron diffraction data acquisitions was done in the stepwise mode with beam precisions. The reason to do it in the stepwise mode because the crystal size was very small, and indeed it was very difficult to track the crystals during the tilting procedure. Example 3, it comes from our work from last year. This is studying a naturally occurring mineral called zaccharinite. This mineral was first actually discovered in Dominican Republic, and it comes as an aggregate with many other minerals. So as it comes with aggregate of many other minerals, it was not possible to do any structural analysis using X-ray diffraction method. But in 2012, it was possible synthetically grow the same mineral in the lab, and the structures was proposed using X-ray diffraction study. In 2019, we have studied the naturally occurring form of this mineral. Sample was prepared by FIB to get an area of interest, which really we are interested to analyze. And then during the EDX analysis, we have seen the second mineral phase very close to the phase of zaccharinite. So, but we focused on the zaccharinite only. So first 3D electron diffraction data was acquired in stepwise mode with precision, and then subsequently an unit cell was obtained and a structures was solved. And this result obtained from the natural occurring mineral matches very closely with the result obtained from the single crystal X-ray diffraction data. But we had some additional observations. Actually, we saw presence of modulations in the diffraction pattern, which we also confirmed by looking in the high resolution images of this material, which actually was not reported, was not observed in the synthetically grown material of this mineral. This result we have published last year in Microchemical Journal. The fourth example, it's one of the most interesting example for us to working with this example. It was actually studying the pigments responsible for the color in a 5th century BC glass amphoras. The sample actually was excavated from south of Greece. First, we have done EDX and EPM analysis to find the chemical compositions of the pigment. And in the chemical analysis, we have observed the natural composition of the silica, that means a lot of silicon oxide, but we also observed traces of titanium oxide, cobalt oxide, and copper oxide. Then we have done sample preparations for the TEM experiment by ion thinning, and we have collected 3D electron diffraction data by doing a stepwise and precision mode. And from the 3D electron diffraction data, we got a primitive hexagonal cell. In the next step, once we have the chemical informations and the unit cell informations, we looked into the structural database, especially from the ancient period, to understand which phase is actually our current phase belongs to. Then we find two possible options. One is the two blue pigments actually found in the literatures. One is the Egyptian's blue, and another one is the Millerite or Sumulite mineral. But our structure is hexagonal, so we discarded the first one. And interestingly, the second one, which is matches with our results from 3D electron diffraction, it is the same minerals is also found in a 1113 BC scarab of Egyptian origin in Sardinia, Italy. As the same mineral was found in Greece, possibly there was a trade route between Egypt, Italy, and Greece in this period, and that's also we have confirmed from the literature, from the other literatures and other literature sources. So, and we have actually studied many other pigments from different glass amphoris, and all of the results we have published in three different journals. So, as all in the previous slides, you have seen that all the structure solution, all the structural refinement has been done in kinematical, assuming kinematical intensity. And with this, we can get a quite accurate structures, 10 picometer accuracy, which is mostly it's required for most of the structural problem. But one can go a step further ahead to improve the quality of the structures by doing dynamical refinement, which I will not discuss in these presentations due to the time constraint. But let's see an example to understand what's the difference and what we can obtain with dynamical refinement. It's these mineral structures were refined kinematically and dynamically against the precision electron diffraction data and compared with the X-ray result. First thing you can see just by looking into the image, once you do a dynamical refinement, there is a better increment of the refined structures with the X-ray structures. Now let's look some of the numbers to better understand the quality of the refinements, because as you always look the numbers to understand our structure solutions. So one thing you can see, the R factor, what the author obtained in the dynamical refinement is much lower than the kinematical refinement. That means we have obtained a much better quality structures, and also you can see that the positional accuracy has been increased. Now the positional accuracy is close to 2 picometer, instead of 9 or 10 picometer in the kinematical refinement. There are many more things one can do actually with dynamical refinement. One can do refine the disorder in the material, one can detect hydrogen atoms, or one can determine the absolute configurations in a structures. I'm not going into the details, but one thing you need to keep in mind that precision is mandatory for doing any type of stable refinement process. And all these works has been published by the authors in different journals, and some of the most important one I have mentioned it here. Now, so what next? What are the future promises for this technique, 3D electron diffractions? In next few years, we believe structural analysis by 3D electron diffraction will have a major contribution, especially for in situ process, as now many in situ sample holders are available commercially, and also I believe for solving structures for macromolecules, and it will be more accessible for all the scientific community. Let me show you the first example where during an electrochemical reaction process, a new phase was formed, and it was possible to collect 3D electron diffraction data during this in situ chemical reaction process. And actually this is the structures of lithium iron phosphate, and more details you can see in these publications. The second example is in protein lysozyme structures. It's a lysozyme structures which has been solved recently from a 3D electron diffraction data in combinations with beam precisions. So from here, I'll finish my presentations, and personally, it's been a challenging and rewarding journey for me to work with different types of material, different challenging materials with electron diffractions. And I'm sure after these presentations, some of you will try your material in the electron microscope and to study the structures, to understand their local disorder. And thank you everyone for your attention, and thanks again for joining this webinar. Thank you.